Okay, so thank you very much for the very warm introduction. My name is Dr. Krishna Puranam. I generally go by Sai. So, in case you guys want to reach out to me for any further communication, just call me Sai. Okay. The doctor thinks sometimes I feel it's like more than on the head. Okay. Anyway, I basically am IPC, as we call it, Industry Process Consultant with Dassault Systems. How many of you have heard of Dassault Systems? The students? Yes. Where did you hear it? This exactly. Everybody asks me, do you design the jets? I mean, I don't design the jets. But then they actually come from the military wing that we have from from the Dassault Systems. I come from simulation. But generally, all kinds of antenna placements that we basically do for lots of aircraft, they basically use CST, which is the software that I'm going to be talking about for a few minutes, maybe about 35 to 40 minutes, especially from the domain of power electronics. But CST is not just limited only to power electronics or EMI, EMC related. It has its spread even in other domains as well. Are there any iPhone users here? Including me? Right? So all kinds of antenna placement that you basically do with iPhone since iPhone 14, they've been done with CST. Okay. So in addition, if you're basically looking at the design of different high-power microwave devices as well, especially if you deal with institutions like BARC, Baba Atomic Research Centre, or MTRBC in Bangalore, or RR in Noida. These are the main places that I can really go to. We use CST for designing high-power systems. But today's talk mostly will be on EMI. So here is so I just want this to be a two-way communication. At any point of time, if you have any questions, please raise your hand and we'll stop. So I don't want to be like teachers sitting here and just preaching. Okay, so we'll actually have a little introduction to CST, and then we'll do a little introduction to EMI, EMC, and we'll see as what's possible with CST. And then we'll have a couple of examples where I'll be talking about conductor emission. How many of you here have heard about CE and RE? Nobody? Great. That makes the canvas blank, so I'll be able to explain as to what it is. And then we'll also look at a radiated emission illustration, which is a customer story that we have from Bosch. So we'll be able to clearly see as to how your real-life simulations can actually help in ensuring that you have a device that works. And finally, since most of the inverters, most of the power electronics devices that we actually deal with come from the T&I, which stands for the transport and mobility industry, I'll also give a little step-by-step approach as to how you perform a full vehicle EMC simulation. So if at all you are basically going to be power electronics engineers, then you should well be aware of what actually awaits you once you cross the gates of this institution. So let's see. Simply, CST stands for Computer Simulation Technology. So it basically is used for solving Maxwell equations. So for all of you guys who are introduced to electromagnetics, you will know that there was one gentleman called James Clerk Maxwell who basically unified the theory of electricity and magnetism with his four equations. Now you basically try to solve those equations for electric field and magnetism. Now, I don't think even Maxwell would have imagined as to what all his equations would actually give rise to. So if you're looking at what all is possible, the large variety of applications that you use electromagnetics in, these are just quite a few, just not going to go into a lot of them, just a couple of them here. So you recognize this person.
That will not work here.
It's not working. Okay. So hi. Yeah. So you see that person? That guy is holding a cell phone near his head, right? So any kind of a cell phone that you design, it will have to meet a specific requirement called SAR, specific absorption rate, which means that which means go ahead, point to the laptop as well. Yeah. Okay. Specific absorption rate stands for how much amount of electric field can your body take in before the tissues start to heat up. So, if you basically go under an MRI machine, you don't want to be cooked in an MRI machine. You just want to come out safe and sound, yet you want to have a good image. Because the MRI machine generates high energy magnetic fields that cause precession of your protons, and then they generate an image. That's a different story, but bottom line is you want to come out safe and sound, and there are specific limitations that any kind of a device would have to meet. This is called SAR, specific absorption rate. And similarly, you also have a specific absorption rate for the cell phones that you use. You cannot keep the cell phone. Even let us say that if you are one of those who keep on having the cell phone here, in addition to having a neck, you don't want to have any problem with your head as well. So, SAR limitations have to be simulated because you cannot ask a person to basically keep the phone in the, on their head. So, what you use something called a phantom. Where you have an image of the human head and you place a cell phone like an iPhone or an Android, you might actually say, and ensure that it is used right. The second one that I can actually talk about is maybe a car. All of us drive cars, and on top of each car, you basically see a small object like the fin of a shark. Right? It's called a shark fin antenna. Now, the shark fin antenna basically it has a combination of 3 or 4 different antennas that are placed, and then they are covered by a structure called a radome. Now, the radome helps in protecting your antenna. In the shark fin itself, there are multiple antennas, and then how do you know where you have to place the antenna on the car? Will you place it on the front bumper, or on the top, or on the rear dicky? Where do you exactly place it? All of these kinds of simulations are done beforehand on an actual CAD model. Now, it's not just limited, so this concept of antenna placement is not just limited only to cars. They're also limited to your phones also. There was one very interesting case where one of the smartphone manufacturers actually had designed the antennas in such a way so that the antennas were actually placed here on this corner. So the minute everybody started holding the cell phones and talking, the calls used to drop. Why? Because the human body, the direct current, it comes with its own sigma and epsilon and mu. I'm not going to tell you as to who the manufacturer is, but just let us say that it's not Apple. Okay. Fine. So, just want you guys to understand that whenever you are solving a critical electromagnetic problem, there are lots and lots of applications because they differ in frequency. The problem itself will demand different solutions. So CST comes up with different kinds of solvers in order to solve the problems. So as you go on further, I think in your 3rd or 4th year of your engineering classes, you'll be introduced to electromagnetic, computational electromagnetics as well. I don't know if that's a course that's offered here. Can madam?
Only EFT. EFT is there. For EC at higher levels.
Okay.
RF.
Right. So basically what happens is you have a problem, you break down the problem into grids, like into small cubes, and on each cube you basically solve the Maxwell's equations. Now, depending upon whether you solve them in time or in frequency, you have the time domain and the frequency domain solvers. And in some rare cases, you might have what's called as a PEC method, where you basically perform the integral solve, depending on different meshing techniques. And then there's asymptotic solver for large structures, which consider the rays as objects that as waves. Okay, so with the CST itself, you have 4 general purpose solvers, which are the first 4, and then you have 20 application specific solvers. And you can nowadays, what we actually see is you are not just confined to the domain of electromagnetics alone. The electromagnetic sources generate heat, and people want to understand as to what is the rise in temperature that comes with this. So what CST can actually do is you can take the heat source and then you can run a thermal simulation as well automatically. And you can set it up so that there will be two-way communication between the data. And furthermore, you can also transfer this result to the limited structural solver that you have in CST to see if the rise in temperature gives rise to any kind of a deformation of the structure. Because that we don't want your cell phone to bend, right? Just because you're using it or you're charging it for it. So all of those studies can actually be done. And then you can also have HPCs, which are high performance computing. You can actually use GPUs in order to speed up your simulations faster. I know that some of GPU stands for graphical processing unit. You also have a video gaming laptop which has a high GPU card. But the regular GPUs here are for application specific. They help to solve large matrix computations pretty well. Okay, so we just talked a little bit about CST, the different solvers, and what you can actually do. And for those of you who are been exposed to coding, you might know that it's easier to run a code where you have that parameters, so that you just change the variable once, and then you want to see that record. Similarly, in electromagnetics also, you basically have parameterization that is present, where any variable, any structures, dimensions can be given as a variable, and then you can perform parametric sweeps to see what is the effect that that variable will have on your structure. And then you have post-processing and a lot of parameterization and optimization as well. And CST also supports Python and GDA scripting as well. So if you are one of those people that are like, I don't want to keep clicking, I just want to write a code where I actually let simulation run automatically. Okay. Any questions till now? That's the very first part of our talk. Yes, madam.
Let's say we are meeting an antenna for 800 stage, and if you want to say that it is over the surface, this part surface is usually PET, and then if we want to run the simulation, and for that tetrahedral shape will be very small. So overall timing will be very high. So we simulator for that surface we are doing.
So you use an approach called the SAM approach, right? The SAM stands for System Assembly and Modeling. So you break down the problem into two parts. One part will be specifically for the antenna, where we use one specific solver, and the second part will be for the car itself. So the car can actually use a different solver considering the field source from the first one. So that's the approach that we would have.
So actually, for every and domain solver,
correct.
And you have so different like integral solver and the ring optics also we are using there. So for which solver will be best to take for perfect?
Yeah, we can actually have that discussion maybe after. But in general, which solver to use depends on the electrical wavelength. So it's not the actual length of the structure, but the actual length in terms of lambda. In terms of L by lambda ratio.
For like previous and all.
Okay.
That will be 1.5 GHz.
Okay.
So for that, like, it will be millimeter or 2 centimeter wavelength filter.
Okay.
And with respect to that, fast surface will be very, it will be very large.
No, but I think we can actually have that discussion maybe after this thing is done. Yeah, we'll have it. Okay. So now that the little introduction that we have, let us come to the actual methodology of performing the EMI EMC design and simulation within CST. So in general, why do you actually have to what EMI EMC? All systems regularly radiate, and one of the things that you would actually have to check is the system that you have designed. It has to work in consonance with the other systems around. So in general, the system that you should have designed should not have any untoward influence on the other systems around it, nor should it be influenced by these systems. So that's what you basically call as emissions and susceptibility as well. So EMI/EMC is very crucial to all kinds of products because they go all the way from kilohertz to gigahertz region as well. So in this example, now this is just a typical chart that I've actually shown. We are considering the deployment of EMI/EMC simulations in the domain of transport and mobility. But then if you basically see, if you actually have if you look at EMI, EMC simulations, generally the trend now, at least we are very happy, is people are thinking of integrating the simulation part right during the design phases. But in the previous years, what would actually happen is they would actually come to the manufacturing part, they would manufacture the design, and then they would actually test it. And then you would see that it has failed to conducted emission or radiated emission. And then people would then basically do a trial and error approach, where they would put some kind of a copper tape or some kind of a sheeting in order to ensure that your sea levels are. But in such a case, the cost of changing your design will be extremely enormous. So it's much better you actually use the simulation during the design phase itself. So if I'm basically breaking down EMI, EMC, it actually comes into two different pieces. One is the emission part, and another one is the susceptibility. Now, in the emission, what you're actually trying to do is there are four major areas: conducted emission, radiated emission, shielding effectiveness, and cable emission. And the susceptibility part, we have ESD, and then you have RI, which is radiated immunity, and then you have ECI and surge. So we'll actually be dealing only with the conducted and radiated emission parts, and I'll also explain just a little bit about the other two during this talk. Okay, so let's skip this. So firstly, conducted emission. Because you guys said you're not used to, term itself is a little new, which is good. So conducted emission means that if you have a device that is, let us assume that you have a lot of devices that are connected to the same power supply. And if at all there is a switching behavior in one of the devices, the chances are that there might be a high frequency spike that goes back into the power supply. And it will travel through the power supply to all the devices that are basically connected. I can give you one example. When my grandmother, when I used to remember, whenever she would turn on the mixer grinder in the kitchen, we used to have an old Noida TV that would just click up for a second. Because there is a high frequency spike that comes. And it travels through and it comes to wherever it is. And especially in the domain of automotive industry, this is very critical because you have lots and lots of power converters, step up, step down converters, buck converters, boost converters, asynchronous, asynchronous converters, and so on and so forth. So you would actually have to characterize that before your system gets certified. And there is always a level there are always standards that are already designated for your CE emission improvement. Your device will not be clear with the stop. Okay, so in CSD, so what we generally do is we start all the way like a bottom to top approach. So you take the model geometry and then you run a 3D electromagnetic simulation on it. And wherever you basically have components, you actually perform a circuit simulation on top of it. So let me give you an example. I know this is a little bit abstract. So that is a step-down converter. It's a buck converter that basically takes a 12-volt input signal and then it basically is giving out a 5-volt output signal. Now, you have multiple converters like this within your PCB board. Let me put it that way. So if I have to actually check whether my device here passes the CE emission, earlier in the olden days, what people used to do is they would make the PCB board that you would actually see, and you would run the simulation, and then there's a device called LISN, which stands for Line Impedance Stabilization Network, which measures the signal that's coming back into the power supply. And then you would then see whether that limit has been breached or has it been met. If it has been breached, then you would have to try to understand where exactly is the source coming. So, with CSD, what you can basically do is you can actually perform an electromagnetic simulation and try to understand as to where this is coming from. So, what you generally do is before the PCB is manufactured, the PCBs actually come in a 3D model. It's called an ODE++ file. Think of it as a file that has all the information related to your PCB. So you take the PCB information, and then wherever you basically have transistors or electromagnetic or lumped elements, you would basically run a 3D simulation first, calculate the S parameter or the behavior of the 3D model, And then wherever you have components, you would connect the lump elements, and then you would run a circuit simulation. Now, one question you might actually ask: why am I basically running a 3D as well as a circuit simulation? Why can I run a 3D simulation on the time? Sometimes your PCB boards are very, very thick. When I say thick, I've actually dealt with PCB boards that are 21 layers thick. So, if at all if you have an demand, and on the I work, one customer had 188 boards. So, for a design like that, if you are actually running a 3D simulation, even for a small change in the component, it would consume enormous amount of time. So what you do is you run one simulation first, get all the information, and then start connecting the components wherever there are ports, and then you will run a circuit simulation, which basically is pretty fast.
Here we have connected basic like lump component and those non-linear element. So this result will be only for experiment parameter, or it will give voltage and current also?
It will give voltage and current also.
Is CST
Yeah. If you use the schematic, it will come. So if you basically, once you connect the schematic, you would actually put in probes at the point where you want to measure the voltage and current, and at that point you would actually get the result, because the CE emission that we're talking about, which is the how much amount of voltage you are basically seeing at the LISN port. So we'll actually see that. Okay, so as I said, you take the PCB model first, and then you basically discretize it, and then you run the complete simulation. So wherever you see those red arrows in the lower half of the figure, that is where all of the ports are connected. And then what you do is you come back to the schematic, and wherever the ports are present, you actually have your lumped elements like inductors, capacitors, and CST can also read in SPICE file system. Let us say that you have a non-linear device like transistor. You can actually use the SPICE model of the transistor also, and then you can run the full simulation. So this result that you are actually seeing, the very first result that you are actually seeing here, that is your, I don't know if you can zoom in and see, but there are two curves, the blue curve and the red curve. The blue curve is the simulation, the result that you get when it is unfiltered, meaning that your EMI filter is not open, it's basically not functional. And the red curve is the measured. As you can see, the more ideal your structure is, the results are more or less basically that. The second part is you have your EMI filter on, where you see that you do not want that high frequency spike that is basically coming in from here, and you can manage it. You can include that EMC filter in your design by talking back to PCB experts, and then you'll see that the result, the spike basically comes down. So the moral of the story is, even if you have a large amount of signal integrity that might actually be part of your design, if you do not pass EMI EMC that design is released, then you will have to find a critical balance to it. And CST can actually give you results like this as well, where at the switching frequency of 488 kilohertz, you'll be clearly able to see the results with and without the filter being on. Now, these kind of results are not possible with the measurements. The measurements will basically know whether your system has passed optimally, but you'll not be able to clearly see where the amount of current density is basically low. Okay, so now that we know as to how a converter works, so we come to the next slightly higher step. Now this is a critical part of your any power design. This is basically called as an edge-to-edge inverter. So you have you basically have six transistors on the top side. Basically have 3 transistors on the high side, and then you basically have 3 transistors on the low side. I don't know if you guys are taking with me. So you have high U, high B, and high W. These are high transistors, and these are basically low transistors, low U, low B, and low W. And then at the end of it, you basically have a model of a motor that is basically correlated. So in order to run the PWM signals, what we have is we have a macro. So So in order to basically run the PWM signal, we have a macro that ensures that this is of course the typical schematic that you would actually deal with. You have your edge range control logic, DC input and motor output. But we now use the typical driving waveform, the CST. And you see that, I have it in this slide. So you have three transistors, one for the high pass, one each for the high pass, and one for each for the low pass. And then you have PWM signal that is basically generated. Now the PWM signal is generated in such a way so that at any point that you actually take, only one transistor in the high domain and one transistor in the low domain will be active. So if I'm actually looking at this signal, at that point as to where the marker is, you see that the green signal, the V is active. So that transistor is on and the signal goes, the motor windings comes back and then it basically closes the loop. And you'll be able to clearly see the waveform basically going to the structure. So with our partners in AD Japan, we actually worked on this model. So all you see is you already see a PCB that is present in that steel enclosure. You actually see it right here. There's a PCB that's present in the steel enclosure, and then you have your cables, and then you have your motor windings, and then the motor load. And then if you see, that's the DC voltage, that's the battery that's coming in, and that's your LISN, which is your line impedance stabilization network. And the output of the LISN goes back to your spectrum analyzer so that you'll be clearly able to see as to what is the signal strength that you're actually getting. Now, the same model, you can build it up within CST itself. You have your entire structure that has been created, and you have your PCB files that have been created. And in the red ones are the ports, and then you put the thing in. And then you run the same methodology that we talked about. You run a tetrahedral mesh, and then you get the results of these parameters, and then you then go to the circuit schematic, connect all the components, and then you run the simulation. And you see that both the PCB measurements A and B are more or less agreeing with each other. The red one is the measurement, and of course the green one is the simulation. There's some slight variations. But that's because we have taken a simplified model of the PCB here. But the more amount of information that you actually put into your structure, you'll be clearly able to see very close alignment. Okay, so that is the second section on conducted emission. I just wanted to So this work has been presented by Dr. Hansen, who's the chief EMI person at Bosch. So we'll get into this overall structure, but I just wanted to show you as to how simulation can help you in ensuring that you have reliable results that would actually affect your final work. So Bosch, when they were actually running the simulations, they ran into one issue where they said they were passing, as you can see, there are four main tests which your design has to pass. You have the conducted emission that we kind of talked about, and then you also have what's called as BCI, which stands for bulk current injection, and then you have radiated immunity, meaning that the device will work even with external interference, and finally radiated emission, which is your RE. Now the radiated emission basically means that if you have a device that you have created, that device should not radiate, meaning it should do what it is supposed to do. It should not in any way give rise to unintended electromagnetic disturbances that could affect other components. So what you generally do is you take your device and then you put it into the chamber that you see. It's called an anechoic chamber. Those of you who will be dealing with antennas, they are very well aware of it. Now the antenna anechoic chamber has lots of absorbers so that if a signal hits it, it absorbs it. It will not give rise to any other effect. So Bosch had this effect that they had designed their rotor, and somewhere there was an issue. They were actually seeing extremely at around, if I can see, I think at around close to 960 to 975, their RE result was very, very high, as you can see. So the green ones that you basically see here, they are your probes. In general, in an actual anechoic chamber, those will be antennas. These will be the antennas that will be capturing the signal system. Basing on those antennas, Bosch backwards and said, look, we seem to be having an RE issue because the top antenna is picking up a signal which it should look like. So our EMC team worked along with Bosch. So what we did is we created a CAD model of the entire motor itself. And once you run the simulation, we actually saw that what Bosch was seeing was
What is the RPM roughly, sir? Any idea?
no, sir. I didn't know.
975 megahertz does not be
So I don't know the RPM, but I can look at.
Okay.
So what I wanted to say is, at around when you have your design very close to how your final output is, we were actually able to see that at 975 megahertz, your H feed was actually leaking through the structure. The leakage was okay, but it was the H feed that was actually propagating through the structure, as you can see in the design that is highlighted in red. And this was only in the front direction and not in any other direction. So from this, we had suggested to Bosch that look, if you basically put good shielding and put your cables through it, there is the shielding would actually stop, the field emission would stop, and so you see in the second structure, there's a without shield and the with shield structure, we are able to see that there is a large reduction in the H field. So Bosch guys were happy with that. So I think they record us. They refer to the work that we basically did in the work that we did. So if I come back, alright. So now that we've had a little introduction to CE of a converter and that of an inverter as well, I just wanted to give a little. I think we have covered the last part in about 4 or 5 minutes because a lot of information, and I think this itself will take about 3 to 4 hours. A lot of detail. But if you're simulating a full vehicle kind of a structure for EMI/EMC, what you need to do is you basically need to start as we did this from the bottom all the way to the top. Because once you put everything into the chamber and at the design phase, you basically do not know as to what is the result. And EMI/EMC problems are very, very hard to debug. So let us say that if you are looking at the overall diagram, so you start from the battery, and the battery gives DC current, and then you then go into the inverter. The inverter will give you the current that will go into the motor windings, and then the inverter that goes to actually looked at. So we're now making the scale a little larger. So instead of you basically having just one H bridge, we now have a combination of 3 different modules which basically perform the functionality of the H bridge itself. So what we do is you perform a 3D full wave simulation. We go into the ports, we connect the lumped elements, and then we give the results back, and we see as to how the grid works. After that, if I'm going to a little more detail, so you basically create that entire structure all the way, and then you see that this is the same schematic that we had actually looked at before. You have 3 for H, 3 high transistors and 3 lower transistors, one for U, V, and W, for high and W, and then we use the macro to create the PWM signal generator based on the specifications that are found in your data sheet. And then what we can see is you try to see that what is the current that finally goes into the motor. Once you are happy with the results of the H bridge itself, then the next step is to see if there is any kind of a filtering that's required. If there's a filtering that's needed, you basically need to take the data from. Okay. You're happy with the inverter and the filter and their combination. So the next step is design of the full power train model. So in general, this is the full power train model that will actually be present in almost all of your cars. If you open the bonnet of your car, then you basically see. They have a lot of screws for air inlets and for fluids and so on and so forth. As an EMI/EMC engineer, we basically do not need all of those teeny tiny details of how the screws are fit and how the grids are and so on. So what we do is we basically smoothen out the model, because the main problem is if your design actually has any kind of sharp corners, then it will take a lot of time meshing. So you do not want to spend a lot of time meshing, you want the problem to be solved. So you would actually use different tools that are present within CST or ATM to clean out the model. Some of them are, of course, the track model simplification that you can actually do. and then you then run a EMI EMC analysis setup for the full power train. So if you see this design, this is very similar to what we had seen. You have your inputs that are basically coming in current power, and then you have the cables that then will go into your IGBT modules, and this IGBT module is basically then going to your motor. Then of course, once you start putting the shafts and everything in, you have drive shafts and you have brackets 1 and bracket 2. This is a very simplified model, but the more complicated modules can actually be incorporated as well. We actually did one design in this with Volkswagen, and we are hopeful that the results will be published later. That's more information. And once it's done, it's not going to be more available. You can then basically see what is the power and the current that is going through the cables, and also through the drive shafts as well, as to how much you are basically seeing. And once that's done, we are happy with number 2, and then the third part comes in. So this is where we were originally. There's the inputs, cables, LVTs, and the motors. The next step is you include the power train, and you're happy with that design. And once that's done, you basically then try to put in the full engine suspension and brake, so that you have the metallic requirements that are generally present as to where your car models, car styles, and needs have to go. Once you are happy running the simulation for that as well, the final part is you run the vehicle chassis. So now the vehicle chassis itself can then be incorporated into CSP, and then you mesh the entire structure and you place your overall structure in work. Please do keep in mind, this cannot be done on a normal laptop. You have to have a good HPC, good workstation also. I'm a little doubtful because the tetrahedra will run into millions and millions, and then have to perform an active machine. So what we suggest is to run a simulation like this, you will need to have a HPC cluster, bunch of supercomputers that are basically connected and can solve this issue. And once that's done, you'll still be able to look at all the overall speed results for the entire structure to see if anything else comes into. Okay, so with that, I bring my talk. I know that I've given you a brief overview on what can be done peacefully. If there are any questions, I think I can take a couple of them before I hand it over to the next speaker.
Long live India and France friendship.